turn it over. And Martha has graciously agreed to join us here for this morning on our virtual retreat. Martha is the Education and Public Outreach Lead for the Solar Dynamics Observatory at NASA Goddard Space Flight Center. So many of you know SDO, so Martha is the EPO lead for SDO out of Goddard. And she's been involved in a number of programs at Goddard and around the country, focusing on informal settings for the public to interact with science in meaningful ways. She's also interested in design and evaluation of informal education and public outreach programs. Prior to coming to NASA in 2010, Martha was a training manager for ProSci Inc., which is a research and training company specializing in change management training, research, and advocacy. Martha has a degree in Russian studies and biochemistry from the University of Colorado at Boulder, and is a returning Peace Corps volunteer, where she had served in the Republic of Georgia with her husband, Julian. Now they live in Washington, D.C. with their dog, Nigel. And Martha is also working on a master's degree in program management at George Washington University. In her free time, Martha enjoys learning obscure Eastern European languages, traveling with a rubber chicken, and shopping for hot sauce. So welcome, Martha. Thanks for joining us today. And I'm going to turn it over to you.
Well, thank you, everyone. For some reason, right now, they've decided to start moving stuff in the hallway, so it might get a little loud on my end, but hopefully not too much. So Goddard Space Flight Center is an active place. They build a lot of spacecraft here, including in my building. So they're always moving stuff around, and that seems to be what they're doing right now. But anyway, I would like to talk to you a little bit today about SDO. And I was asked specifically to talk about some of the new things that we've learned with SDO, and also some of the non-AIA parts of SDO. And AIA being the one that most people are, the instrument on SDO that most people are familiar with. It is the instrument that takes all of the very, very lovely images of the sun that have been so popular. And I will say it was quite a challenge to stay away from AIA, and I didn't succeed completely. So I have a presentation. I have put it on the WIGIO site, along with many other files about which I will be talking today. And Nancy, so I put the PowerPoint presentation on my screen and then share my screen?
Yeah, that should work.
I can do that. Yeah. All right. All right, so that.
You might have the option to choose share desktop or just share the particular application. So it's up to you.
Okay, let me put this into view slideshow. Although that's not going to help that much. And then I will share. All right, so are you guys seeing my desktop now?
Yes, we can.
Okay.
I can see you.
I will start slideshowing.
Yeah, and I can see that, the PowerPoint.
Fortunately, I can't actually, the people are in the way. All right, there we go. Okay, so what is new with SDO? We've got a lot of new and exciting science that's been happening over the last 3 years. SDO, as many of you know, was launched in February of 2010. So we have just a little over 3 years of data, which is a lot of data because we get 1.5 terabytes of compressed data every day. So you can do the math, and that's a lot of data. And we have so much data that, you know, there's data that people haven't even looked at yet. But one of the nice things about SDO is that they have it was part of the project to make sure all of the data was publicly available, and we've also worked very hard to make sure all of the data is publicly available almost immediately. So I have included some pictures today of today's sun, and that's one of the really cool things that I like doing with students and teachers is showing them the sun that is happening right at this moment. So it's also very exciting for us because we get to, every once in a while, something will happen and we're watching it as it's happening. So we'll have a prominence eruption or a flare, you know, some of the longer term events or longer time frame events, and we'll get to see those right as they're happening, which is cool. So one of the very neat things that we've been able to do with SDO, and we've only had 2 comets, but we weren't expecting to have any comets, so 2 comets is very cool. We have seen 2 comets with the Solar Dynamics Observatory. You may know that SOHO has seen many, many comets in the coronagraphs, but SDO has seen 2 comets. The first one was in, I'm not even sure when the first one was, but the second one is called Lovejoy, and it was in December of 2011 that we saw that, and that's the picture that's up there on the screen. That's Lovejoy coming back around the backside of the sun, and it was very exciting. But one of the very interesting things that we have done with this is the comet group, so people who study comets, and the solar group have actually gotten together and have been working on using comets as solar probes and how comets can be used to study the magnetic field, how SDO can be used to study the makeup of comets. So we're actually using spectroscopy to determine the chemistry of comets, or of these particular comets. One of the interesting things has been comet people and sun people don't speak the same science language. So we've had meetings of those 2 groups coming together and really trying to figure out how to communicate with each other about the science that's going on, because they really do speak, they talk about totally different things. So many of the documents that I included on the website were specifically about comets. We have a scientist here named Paul Bryans who's working specifically on comets, comets that are being viewed by the Solar Dynamics Observatory. And I put a paper of his and then 2 posters. The paper is a little high level as far as there's some chemistry in there and a lot of talk about physics, which is good. It's a very scientist-oriented paper. But the 2 posters, one was at AGU and one was at one of the SDO science meetings. The 2 posters are actually very visual. They have a lot of information about how the comets are being used, how we're looking at them, and what we're doing with them. One of the very exciting things is that sun-grazing comets are actually a pretty regular occurrence, and we've got another big one coming up called ISON, and we're expecting to see that with SDO as well. So we'll be keeping an eye on ISON for Thanksgiving 2013, exactly on Thanksgiving. So not the best day to be running comet events, but we'll go with it. So one of the ways that, one of the things that you can do with comets in your classroom is it's a really great way, because of this new comet viewing, it's a really good way to introduce spectroscopy. It's really being heavily used to study comets, sun-grazing comets with SDO. Comet ISON is we're still a little bit unsure of how it's going to look in SDO, but we're hoping for a good show. It's much, much larger than Lovejoy was, and it is I mean, it's so large that people have seen it and are already watching it. It's been seen by Hubble at least once. I think they were going to point Hubble at it one more time. And so it's an exciting comet just from a comet standpoint, but it's a really exciting comet from a solar comet standpoint. And I forgot to mention, if anybody has any questions or comments or anything, feel free to interrupt me. I cannot keep the chat window, so
I'm keeping an eye on the chat window, so we're going to record some of the questions. If there's any pertinent to exactly what you're talking about right now, I'll interrupt you with them,
okay.
And otherwise we can either talk about them afterwards, or if you want to take them away and have a look at them, and then you can post answers on Wigio later on.
Okay, great. Thanks.
There's also a 30-minute question-answer session following your presentation.
We can do that too. Okay, so this is a very exciting, and I hope that this video works. It does. Okay, so EVE is another instrument on SDO, and EVE has been used. So one of the things I like about EVE is that it's a graph. It's actually many, many graphs, but it is a graph. So, and you can download the data into Excel, so it's something that you could utilize in your classroom quite easily for graphing data. But one of the things, so this particular video here, and we'll watch it a couple of times because it's very interesting. So this is research that was done by Rachel Hawk. She was at the University of Colorado, but now she is at the Air Force Naval, or the Air Force Lab. It's not the Naval Research Lab, but it is the Air Force's equivalent of that, which I can't remember exactly what it's called. But anyway, she was at the University of Colorado, and this was her doctoral dissertation, was looking at flares in EVE, and these are two M-class flares, M1, so not huge flares, but they are the exact same class. But you can see, so the red line is the left-hand flare, and the blue line is the right-hand flare. And you can see that the irradiance, so EVE shows the irradiance. So the irradiance in each spectrum, or each wavelength, is different. They're different from each other, but they're also different flare to flare. So let me show this video. And it's a little hard to see what you're looking at exactly, because there's so much going on the screen, so I'll play it a couple of times. All right, so one of the things that you could do with this then is to go look up the EVE data, go find a flare, and see if you can recreate this same information. So what we've learned from the EVE and AIA comparisons is that even very similar flares are different. One of the things that EVE has shown, and they didn't know this before, was that some flares, not all flares, but some flares have two peaks in the EVE data, and actually the second peak, which happens significantly after the flare, releases more energy than the initial flare. So that's a totally new piece of information that SDO has given us. I think it's cool because graphs are easier for me to read than, looking at pictures. It's easier to see what you're looking at. Also, I know that it's part of the standards to use graphical information and data. So this is a really good way to use the images from AIA, which are very attractive and easy to see when something is happening, and then use the graphs from EVE to really measure, to put some measurements to those images. Another, this is actually, so lunar transits happen twice a year on SDO, and we've always thought they were really cool. People really like lunar transits. They're one of our most popular topics. But one of the things, so if you look very closely at this lunar transit, you can see some lumps on the bottom of the shadow. It's not actually a shadow, it is actually the moon. And those lumps are actual moon mountains. They're lumps on the moon. And until very recently, we hadn't done anything with those lumps on the moon. And then what we did was we grabbed some LRO data. And LRO is a lunar orbiter. It's actually called the Lunar Reconnaissance Orbiter. It takes great images of the moon. And we have matched the SDO moon lumps to the actual moon lumps. And we've mapped them out. So that's something that you could do in your classroom. You don't have to use the data. So this is the data from this last lunar transit, but since there are several lunar transits, and actually we are looking at different parts of the moon with each transit. So the fall transits are a little, are different, is the different area of the moon. But I thought this might be a cool project to match up the moon mountains with SDO moon mountains.
Martha, can I interrupt you just for 1 second? Just
Sure.
for 2 things. First of all, welcome Debbie, but would you mind putting your microphone on mute because we can hear your conversation? And second of all, Jim has a great question here. You might want to postpone it to later, but he's interested in, given that you're talking about the transit of the moon here, was SDO able to see the transit of Venus last year?
Yes, we were. I didn't include it in the presentation, but we do have loads and loads and loads of great video from the transit of Venus, and that was a very exciting day. The SDO science team worked very hard to create special data packages. So we actually increased the cadence of the spacecraft for the Venus transit. So we got more images than we normally do. We also took images, so we took images at a quicker cadence, and they did that actually for science reasons, for instrument calibration on the spacecraft. But we did get some really great movies from the Venus transit, and those are available on the SDO website. Or if you Google Venus transit SDO, YouTube videos galore from the Venus transit. So the next set of slides, one of the things, so AIA, many people are familiar with images, but I wanted to make sure that everybody knew that it's also possible to get a lot of the science information from AIA, or information about what AIA is looking at in each of the wavelengths. So I have included in the following slides the wavelengths, and then what we're looking at, the temperature, that kind of information, and then also an example of what we are seeing there. So these two websites are also further, they're in the resources page of this presentation, so don't worry about capturing them at the moment. Also, one of the nice things about AIA, and one of the things that might be good for students in the classroom, is the images from AIA are the ones you see in the news. So if you see a picture of the sun in the news or on a magazine, like for example, this one, these are all images from AIA. So it's one of those things that it's easy. You could bring up magazine covers and articles, and those are the images, and they can play. Your students can play with this data as much as they would like. So these are two pictures. I wanted to include the one on the lower right. That is an image that we have superimposed the magnetic field lines on, and every single one of the data pieces from SDO has those magnetic field lines, or has an image. It's called a PFSS file. So when you go to the data page on SDO's website, you can get those PFSS files. So you can talk about magnetic fields. It makes it a little easier to talk about the magnetic fields. So each of the wavelengths tells us something different. This is the one. HMI also has a more accurate sunspot picture. So this is the visible light. It shows us the surface of the sun, or the photosphere. So this is just a little bit above the photosphere. One of the cool things is that you can see flares and some loops. If there's a nice big flare, you can see some loops in this, in the 1600. So this is the far ultraviolet, but not extreme ultraviolet. So I'm just going to go kind of quickly through these. I have included this presentation on the website, so if you want more information, all of this information is available on the SDO website, including what we're looking for in each of these wavelengths, and the temperature and what the ions are that each of the wavelengths is looking at. So this is the 171, very popular. These two are the most popular as far as getting really cool pictures from. The 304, which is 304 angstroms, or 30.4 nanometers, is the one that you see all of the filament eruptions and the prominence eruptions. Many of the slow-moving CMEs you can see from here as well. Then this one has all the lovely loops. I think this one, the picture on the right, is actually called Lovely Loops. The 193, great coronal holes, and actually the images on the upper left of all of these are from today. So we have a lovely coronal hole happening today, and you can see that really well in the 211. This is a good flare. The 335 is a great flare finder. Same with the 131. And the 94, often it looks very blurry and sort of pixelated, but really what the issue with that is there is just not enough information in this wavelength to make a super, I mean, these are the highest resolution, but there's just not enough data to make a particularly sharp-looking photo or sharp-looking image. This should be a movie, but I included the movie on the Wigeospace because it's not very exciting this small. But you can make videos of the magnetograms, and you can actually see the magnetic field moving. I don't think you can really see it very well here. But you can see the magnetic field as it moves around, as it changes. So I included a link to the video as well. This is a part of the Eve instrument. It's called SAM, and this is the X-ray, and this is today's X-ray image. So you can see we have quite a few active regions, and then that big coronal hole, which is up in the dark spot on the upper left of the sun. So we use that. You can really see flares quite well with this. It's showing a lot of irradiance.
Martha, can I disturb you there? We're getting some questions about what is a coronal hole, so maybe you could just take a step back and
Sure, sorry. Coronal holes, I'll actually take you to an image. So that dark spot is called a coronal hole. It is an area where there is a low level of magnetic field, and actually it causes what we call the solar wind to basically flow out of that hole. And it's one of the major causes of non-activity linked aurora and things of that nature. So a lot of particles are moving out of there in the solar wind.
And the solar wind is known to be a source of, the coronal holes are known to be a source of the solar wind, and I had tried to write a description in the chat there, so just let me elaborate real quick. I had said that they act like a funnel. So under normal circumstances, the magnetic field on the sun loops back on itself, so that's why we see all these loop structures on the sun. But in coronal holes, the magnetic field doesn't immediately loop back to the sun. The loops are so huge that they reach out beyond the planets, and so material from the corona gets funneled out. It's a bit like a straw that's stuck into the surface of the sun. It means that material can flow freely out, so there's no material there to be bright, which is why they look dark. But they're only dark in some wavelengths, so they don't appear dark at all wavelengths, which is interesting.
Right, so I'll go back a couple. So this is the 211, and you can see the coronal hole very well in the 211, and you can see it in the 193. But you cannot, it doesn't look dark at all in the 171. And you can barely see it in the 304. So like Claire said, it's really only visible in some of the wavelengths. And remember, these are all extreme ultraviolet light. All of the AIA images are extreme ultraviolet. All right, so here are some resources. I've included a little screen clipping from the SDO website, which is that first website. So when you go to this, you'll get to a page that is sun, right, the latest image of the sun. So the sun right now, minus 15 minutes or so. And then you can push this little, the little icon, which will give you the information about that particular wavelength. So it'll give you the temperature and what we're looking at and what we are trying to see with it, and where in sort of the layers of the corona it is, or the transition region. The comets, like I said, I loaded several pieces of information and documents on the geosite. The EVE AIA data from the flare comparison, if you go to the Lockheed Martin events site, which is that first link, you can find any, it's not just for flares, you can actually find any event that you would like. So if you're looking for a flare, or if you're looking of a particular size, if you're looking for a CME, it will tell you, you can put in dates, you can put in exactly what you're looking for. The only caveat is it's extremely sensitive. So for example, today, even though we have had no flares of note, there were about 20 flares listed for today. So it is very, very sensitive, but you can go through the list and see what the actual size of flare there was. And then the EVE data that can be downloaded is available at that second website. So what I was envisioning happening with this AIA data is you could go and find an event and find the AIA movie to go with it, and then you could go to EVE and download the data for that particular time period that the flare was happening.
Yeah. I'm sorry to interrupt. This is Andy. I don't know if you heard the tone or not, but we are at, that was the warning that we have about 1 minute left.
Okay. Don't we have a half hour of question and answer after that? Okay.
Yep. Just wanted to honor that time.
Okay. I am almost finished.
And I know I can tell people have lots of questions because this is just rich and beautiful.
The second to last part, the lunar transits, that is the SVS website, which is the Science Visualization Studio here at Goddard. And that is actually a great place to go if you're looking for full resolution images. You can get them off of the SDO website, but if you're looking for something very processed and very lovely, this is the site that's put together by the Office of Communications. So if you just go in there and type in SDO, you can find a lot of great images. This link in particular is to the lunar transit images that I showed you before. That would be the best place to get those images. You can get them at full resolution, which is 4K by 4K, although not sure that the LRO data is the same, so it might just be 2K by 2K. And then the SDO website, we have an EPO, or an Education Public Outreach section, so that's that. And if you are not familiar with the NOVA Sun Labs, or the NOVA Sun Lab, I would really recommend that. It has a great tutorial on how to look at the sun, how to do sun activities. It's geared toward middle school and high school students, so it's a really great place to start if your students are interested in doing some labs, or if you would like your class to do some labs. Here is my contact information. And we do have a Twitter feed specifically for educators, and that is that at NASA SDO EDU. All right. I am ready to answer questions, and well, I'll leave it up there in case we need to go back to a specific slide.
That'd be great. That'd be great.
Sandy, would you like me to go back through and read some of the great questions that were posted on the chat, or to start with some live questions?
I was just going to ask you the same thing, Claire, so you must have been reading my mind.
A great mind to think alike. I think we should go back and look at some of the chat questions, just because they were posted live, and then after that we can kind of open the floor. I think they might generate some great discussion.
Perfect.
And I will, you know, if I can't answer the question, I will find the person who can and get back to you all.
Yeah, I have a recording of all the questions, so we can keep these and make sure they all get answered eventually.
Great.
So one question that it's sort of a group of questions, I'll try and put them together so we're not reading every single line. There was questions regarding before SDO, did we know there were sun grazer comets, and did SOHO have any insight into this, and did SOHO not try to figure this out, I guess using their coronagraphs? Okay.
So yes, we did know there were sun grazing comets, and actually SOHO, that was one of the very cool things with SOHO, is that it was never intended to be a comet spotter, but with the coronagraph, it's possible to see all these comets come in. But the issue with SOHO is that we never saw them actually coming close into the non-coronagraph part, so into the EUV imagers of the sun. So we did see we've seen over 2,000 comets with the SOHO coronagraphs, but we have never seen a comet with the EUV, so extreme ultraviolet imagers. So we've seen 2 now. The issue with SDO, and if you go to, let me just go to that comet, you can see that is a very small portion of the sun, and that is a very small comet. So SDO has a huge image, and it's extremely high resolution, and the cadence is very, very fast. So this particular image is in the 171 wavelength. So this image, an image in 171 is taken once every 12 seconds. And SOHO at its fastest cadence was taking one every SOHO was taking one every 12 minutes, not 12 seconds. And then stereo takes one every 3 minutes or so. So the fact of the matter is, we can see these comets in SDO that we could not see in either stereo or SOHO. Although we are hoping to see the ISON comet with stereo, because it will have perhaps the best view. Stereo behind will have the best view of the ISON comet, because it will come directly between stereo and the sun. So we're hoping to get some images, but really the cadence and the resolution of SDO has enabled these comets to be visible.
Thank you. Does anybody have any further questions on this before we move on? Give it a sec just in case people are trying to unmute their computers.
Hi, here I am. I was wondering if you could elaborate some more on the spectroscopy and how you're using it to analyze data.
Well, so specifically with comets, or specifically with SDO, or?
Both, either.
Okay. Well, so I would encourage you to go look at those files that I put up on the spectroscopy of the comets.
Okay.
It is not something I'm particularly familiar with. I did talk to Paul about it, and I know that they're working very hard on it.
I can elaborate a little bit, Martha, if you'd like me to.
Okay, great. Thank you.
I was actually a part of that very, very initial group of people who started working on this, and then I got sidetracked. So the way comets can help us understand the sun is because they are they're essentially like little probes. So if we can identify the material that's inside the comets, and then we can look at the comet and we can see how it changes as it approaches the sun. So how quickly does its tail go away? How quickly does it start to ablate the material inside of the comet? And you can look at the comet itself, and you can take spectroscopic images and just data in general, for example, from AIA and EVE, and by looking at how different elements, so spectroscopy refers to the use of spectral, usually emission lines when it comes to the sun, and it helps us to identify things like density and temperature and what we call emission measure, which is like how much of a given temperature is present in a single volume of material. And so by studying the spectra coming from the comet, it means that we're able to better identify different quantities inside of the solar corona. So it's not a trivial thing. It's something that took a huge team of people many, many months to figure out. There's an awful lot of atomic theory that goes into this, but it's basically, because this thing is flying through the corona in real time, which we can't normally do, it means that you're able to use the comet as like a mini probe. So you don't have any don't have any input on what the comet looks like before it goes in. The comet is the comet, and you just got to accept that. But you can track how it changes as it goes through the corona.
And there are two posters that I put up there. One is the AGU poster, and one is called Poster Lovejoy. And actually the AGU poster, which is called poster_AGU 2012, has a lot of information about the different spectral lines that they're looking at, and the elements that they have sussed out of the comet based on the spectroscopy.
It's been really quite revolutionary, and I actually think they got a science paper out of this, or it was a Nature paper perhaps. It was a really big deal in the solar physics community when this sort of field emerged.
And another cool thing with the comet is that you can, beyond the area that we normally can see, like loops of the magnetic field, we can see that the comet's tail is being moved by the magnetic field of the corona. So that's been another kind of exciting part of the comet bit. And as far as spectroscopy in general, with with SDO. SDO looks at all of these different wavelengths because each of the wavelengths of light shows us a different temperature, well, shows us a different ion, usually an ion of iron is what we're looking at in most of them, and those represent different temperatures. And with those different temperatures, we can see how these ions cool and move around. So we're able to, and let me go to this, I'm sorry. This image on the upper left here is it's a 3 wavelength composite, and with those 3 wavelength composites, though they are very lovely, they also show us sort of a 3D image of the structures of the sun in different temperatures, or different temperatures showing us sort of the structural aspects of the solar corona. So that is how we're using spectroscopy just in general with the spacecraft.
Are these the only 3 types of radiation that the SDO gathers, or does it gather additional varieties?
So it looks at visible light, ultraviolet light, and X-ray.
Okay, so that's it.
Those are the 3. Yeah.
Okay, great. Thank you.
Okay, so we have some more cool questions. There's 2 from Sally that I want to read out. The first one is, can this be coordinated with the photos of the moon from MoonCam Grail mission? So this was back when you were looking at the lunar, the pictures of the moon imposed on the sun.
I will have to get back to you on that.
Okay.
I do know that it actually, I thought it was easier to make this image than it was. I contacted the people who created this image, and it's actually a little bit difficult. So I'm not sure if you could use the, was it Grail?
Yes.
I'm not sure if you could use Grail. This was specifically LRO, but I will get back to you on that.
Okay.
Well,
and then
just briefly, I would say that my guess is from working with this that you could, but LRO's purpose was to take much closer and high resolution pictures, and whereas moon cams are great, but they are not as precise as LROs are.
So Sally's other question then was about the stereo mission. So maybe Martha, you could elaborate a little bit on what the difference between SDO and stereo is and how their data are compatible.
Sure. So SDO is positioned just above Earth. It's actually in geosynchronous orbit right above, well, sort of right above White Sands, New Mexico. It has 0 memory. Well, it has about 15 minutes of memory on board. So it has to stay right above White Sands, New Mexico, which is where its data downlink is. And so it is there. So if you can imagine sort of the solar system, or at least the Earth's orbit. So SDO is where Earth is, and stereo has 2 spacecraft. One is in Earth's orbit, but in front of Earth, and one is in Earth's orbit, but behind Earth. So they're all moving. The one that is stereo A, which is stereo ahead, that one is moving just a little bit faster than Earth, and stereo B, because it is behind, it's just a little bit, the orbit's just a little bit wider, so it is moving a little bit more slowly around the sun than Earth is. So basically they started out at Earth, and then over the last 5 years, I believe it's been 5 years, they have moved apart. And there was a moment of time about a year and a half ago where stereo A, so the ahead one, got to the far side of the sun. So basically with SDO and the 2 stereos, we can create a full image all the way around the sun. So stereo B takes the images of the the stuff that is out of the left side of SDO, and stereo A takes images behind the sun. If that makes any sense.
So Martha, I just posted a website link that is the Where is Stereo site, and so you can play with the dates. You can change the date in this if you go to the Orbiter tool, and you can see the stereo spacecraft as they move from the sun, or sorry, from the Earth away from the Earth's orbit in a circle around towards the back of the sun.
Right. So now, unfortunately, what's happening is between stereo A and SDO, a bit of a hole is opening up again because stereo A is moving away, moving closer on the other side of the sun. So it is, they're really a great tool. And so actually right now we can see what's happening on the backside of the sun very easily. The one issue with stereo, because it is now on the other side of the sun, is that the data takes a little bit of time to get to us. So that's one of the, it's not quite as quick as it was when they were a little bit closer.
Okay, so then our next question came from, this was sort of a statement that I think is worth elaborating on because it's very important. This came from Jim, and he suggested using Wien's law to calculate the relationship between temperature and wavelength of AIA images. So is this something you want to talk about a little bit? It's something I can elaborate on also if you'd like me to.
I would like you to, thank you.
Okay, so with Wien's law, basically you're assuming that what you're looking at is a black body. So it's a law in physics that you can use to relate temperature to wavelength. It's an equation that you can apply. However, when we're using AIA data and AIA images, because we're not looking at a black body, although the sun can be assumed to be a black body at its surface, as we go out into the corona, the conditions become very, very extreme, and it's very highly ionized, which means that the assumptions that you have to apply when using Wien's law go away. And so it means that it's much more complicated to be able, it's much more complicated to figure out the relationship between temperature and wavelength, and actually requires supercomputing atomic physics codes in order to do so. So it's more of a word of warning. If you're going to be using these images in your classroom, I wouldn't recommend having one of the tasks that you do with your students being calculating this relationship, because it will just lead you down a rabbit hole. It's not a good idea. So I just wanted to use this as an opportunity to dissuade people from that activity. Although it would be very fun if it did work out, it would be great, but it's not a good idea. However, the temperature that each of the pass bands, the wavelengths you see in AIA, they have been calculated and they're quite well known, so they're available. So I can look them up later and post them onto the Wigio or onto the chat site or something like that.
And that information is available on the SDO website in the info boxes with the wavelength.
Mm-hmm. But it's just, I don't recommend trying to calculate it because
right.
It won't.
Yes. So the temperatures that are listed there are accurate ones, not ones that I calculated.
Yes. I wouldn't. I don't know if any of us could calculate this, given that it requires some pretty impressive atomic physics codes. And in actual fact, this is sort of an elaboration, I guess, but it's actually something that scientists don't understand. Some of the passbands. So the 94 angstrom passband, which is the really, really hot stuff, it's usually colored kind of a mint green color in the pictures. And that passband is not well understood. So the temperatures that are generally used in association with that wavelength are, there's a pretty huge error on them. There's a pretty big ambiguity as far as the understanding of that goes. So it's an active area of research for scientists, is trying to figure out exactly what the temperature is. And it's because we can't go to the sun, and you have to make all of these assumptions and use atomic physics codes to be able to reproduce this. But if you don't get your codes correct, then you don't get the right answer. And so even a very small deviation could give you a huge temperature difference. So it's very subtle.
Thank you.
Yes, Jim, forbidden transitions. Yeah, exactly. Jim has just posted in the chat window, forbidden transitions. So that's all part of it. Is given the high, the very extreme circumstances of, first of all, a highly ionized plasma, as the corona is, but also the presence of the magnetic field throws everything out of whack. So that's why the corona is an area of difficult study as far as that goes, and that's why, to go back to the earlier question, why spectroscopy is so important. Okay, so I think that was, unless more questions have come in the last few minutes, I think they were all of the big sort of questions that came up during your talk. So maybe now is a good time to open the floor to general questions from anybody on the phone right now, if you have other questions for Martha. Don't forget to unmute your microphone before you try to speak. Anybody? Any questions about SDO or AIA or other missions or anything like that? How you can use it in your classroom? Now,
well, and I will say one thing. I didn't touch on HMI, which is their instrument, and actually I didn't touch on it very much because Debbie is talking to you this afternoon, and she is the HMI EPO lead. So if you have questions about HMI, or HMI does all of the magnetic field studies for SDO. So it's a really great instrument for magnetic fields and studying magnetic fields. So if you have questions about how to utilize HMI, Debbie would be a great person to ask. Does SDO feed spaceweather.com? I see this question. As far as what? Info? So SDO is part of a whole series of spacecraft, satellites. The job of space weather prediction when it comes to Earth is NOAA. So the National Oceanic and Atmospheric Administration is responsible. That is their duty. SDO and NASA are responsible for making sure that their assets, not SDO's, but NASA's assets, are protected. So as many of you know, space weather can have a very serious impact on spacecraft and also astronauts, the the electric grid, many other things. So NASA is responsible for keeping their assets safe. So all of the astronauts, the space station, all of the spacecraft that are in space, that's NASA's job. And NOAA is responsible for making space weather predictions for Earth. So that's kind of how that works. And spaceweather.com gets information from all of those areas. They also, spaceweather.com, it also utilizes, they have a lot of information from international sources. So the actual sunspot number has been coming from the Royal Observatory in Belgium for years, hundreds of years, 100 years. So there is a person whose job it is to count the sunspots, and that person's sunspot number is what goes. That is actually a kind of interesting task, is to compare what you think the sunspot number is with the sunspot number that is from that day, because there's a whole lot of grouping that goes into that. And anyway, so that's kind of an interesting task as well. Anything else?
There's John's 5-minute mark for us.
Okay, thank you.
There was a question earlier about where's Camilla? Wendy, I didn't know you have Camilla.
I do not have Camilla. Camilla is currently, I would guess, in California. She is on a travel stoppage like everyone else at NASA. So Camilla she's everywhere most of the time, but her support staff is out of Stanford University. But I have traveled with Camilla, and it is very exciting. Oh, good.
I'm
So
Camilla's friend on Facebook.
Debbie has Camilla, and she will bring her along this afternoon.
Okay.
Along with the iris, I'm trying to remember.
Colors?
Colors, yes, that's right. Camilla and colors.
Camilla is our rubber chicken. She is very special, and she is an outreach specialist who has been instrumental in helping SDO to get the word out to people all over the world. So she's been very helpful for us. She's the SDO mascot.
So there's a great question here from Jane. Jane, would you like to ask it yourself, or will I just read out your question?
You can go ahead and read it.
Okay, so Jane is asking, SDO gathers UV, X-ray, and visible radiation. Does anybody know specifically what information we gather from analyzing each type?
Each type of
radiation, so UV versus X-ray versus visible.
Well, like I was showing, actually it's very easy to see with something like AIA. So the visible light, you can see a totally different sun than you can see in the extreme ultraviolet, for example. So with the visible light, we're seeing the photosphere, which is the surface of the sun. So we can see sunspots. This is the sun that, this is the sun that Galileo was seeing. This is the sun that Benjamin Franklin was seeing. Until we were able to develop telescopes to get outside of our own atmosphere, we were not able to see much else besides the photosphere. With the extreme ultraviolet and ultraviolet, we can start seeing different elements of so this is far ultraviolet, not extreme ultraviolet, but we can start seeing the area above, sort of above the sunspots. We can start seeing the magnetic field with these. We can start seeing some of the loop structures. This is the upper photosphere, which is the upper layer. And then we start so as these get hotter, as the wavelengths get a little bit shorter, we can start seeing the area above the photosphere. So we're actually looking at what you could consider the atmosphere of the sun. So starting at the photosphere and heading out to the corona. So with each of these different wavelengths, we are looking at a different area, a different temperature of the sun, or a different temperature of the material that is in that area. And actually a different, different ions in each of these wavelengths as well. And with each of these, we can see different features. So in this one, we can see filaments and prominences, and but flares don't look particularly good. And we can't see the sunspots at all, but we can see the active regions above the sunspots, for example.
And then what does X-ray capture?
The X-ray captures soft X-ray, the green. So what we can see is flares and active regions in the X-ray. So this is also X-ray, soft X-ray.
And Martha, can I step in here? X-rays are one of the tools that we can use in order to identify how the emission on the sun gets to be so bright, because it is basically a tool for helping us understand particle acceleration on the sun. And using SDO in collaboration with other instruments such as Fermi and RESI, which study from the edge of where SDO observes all the way up to really, really high energy X-ray and gamma rays, putting all of these instruments together can really help us to understand the story of what happens, especially during a solar flare. So it's a way of viewing particle acceleration, which is difficult to observe under normal circumstances.
And with each of these emissions, it would be hard to put the story of the sun together with just one or two of these. We really do need a full suite of wavelengths and information about the emissions to really see what's happening. So that's one of the really interesting things about having a suite of not just SDO instruments, but like Claire was saying, RESI, to put the whole story together, we need all of the wavelengths, or as many as we can get.
Which is why there's so many solar instruments.
Indeed. So I think my time is up. If anybody has any questions, please feel free to contact me. If you need anything, please feel free to contact me. If you have any questions about what I put up online, I'm happy to answer those as well.
Mm-hmm.
This has been really, really great. Thank you so much, Martha. It has just been very, very just amazing all around.
Thank you. I'm not sure how to unshare.
In the top corner, somewhere on your screen, you should have a small window that has people's faces in it, and it has a red button at the bottom that says Stop Share.
Look at that. There we go.
Lovely. Well, thank you.